Okay, this is regarding the hints for lab 3. Okay. So in lab 3 we were asked to make a Neos 2 processor with a RAM of 8192 bytes, and we were asked to connect a clock, a reset, and then we were asked to connect 8 LEDs at the output, and then we were asked to connect a green LED, a single green LED, and then we were asked to connect two GPIO pins, one as an output from the Neos processor, one of the output device, and there is another GPIO pin somewhere outside for some reason. And we were asked to connect a push button, and then we were asked to connect a counter. Okay, so the counter input is the clock input of the Neos processor, and the output is given as one of the device input to the Neos processor, and we are also going to connect this counter output to the GPIO pin 2. So this is a setup what we are supposed to do. Okay, now in this problem we were asked to check what is the polling latency that occurs for servicing a rising edge of this counter device. Okay, now this push button and this counter are the two devices, which input devices which the Neos processor is going to poll, and the service for this devices like the push button. When you press the push button, you need to toggle this green LED over here. So first time when I press the push button, it should be on. The next time when I press, it should become off, and so on. Okay, and then the counter. Now the counter input is the clock, which is of 50 megahertz. Okay, and then they have told us to make a 20-bit counter. They are telling us to make a 20-bit counter and connect the most significant bit of this counter to this Neos input. Now, so this 50 megahertz clock will be divided by 2 power 20 times. So if you see the frequency of this most significant bit, you can see that the 50 megahertz is now divided by 2 power 20. That comes around 47 point some megahertz. Okay, so the output which is coming from this counter is of in the range of 47. Sorry, slip of me. It's of 47 hertz. Sorry, it's of 47 hertz. Okay, let me take this. So the output which is coming from this most significant bit is divided 2 power 20 times by this counter, where the input is 50 megahertz. So the output is of 47 hertz. So every 1 by 47 hertz of time, that is, you will get a rising edge to this. So whenever the Neos processor gets a rising edge to this port, we want the 8 LEDs to count the rising edges. That means for the first time, for the first rising edge, I want the output to this port is going to be just 1. So if I say it's an 8 LED, so if it is 8 LEDs, then for the first rising edge only the first LED should glow. Okay, for the next rising edge, so the count is 2 now, so the second LED should glow and the first LED should go off. For the next rising edge, the count is 3, so the last 2 will glow, and so on. So whatever the count of this rising edge this Neos processor is going to read in this port, we want to display them in terms of 8 LEDs over here. So this is the problem given to us. Now we are going to further calculate how much time the nearest processor is taking to execute this count operation or to respond to these 8 LEDs after it receives this rising edge. Okay, now just I'd like to slightly comment on this counter. So we were actually asked to connect a counter, right? So it has a clock input and we are told to connect the most significant bit. Now if I say a 3-bit counter, that means I count from 0 0 0 0 0 1 0 1 0 0 1 1 1 0 sorry 0 0 0 1 0 1 1 1 0 and 1 1 1. That means I start counting from 0 and go up to 7, so 8 counts. Okay, so if you look into this most significant bit of this count, for every, so if this is the clock of this counter, okay, now if you look into the most significant bit for every, so every rising edge I'm going to make a count. So if you look into this, for the first 4 cycles I'm just going to have 0, and then for the next 4 cycles from this I can say it's going to 1. So again this is going to repeat. You can readily see that the frequency of this clock, which was given as input for the 3-bit counter, when I look into the most significant bit, I can see that this clock frequency has now become, has got, the frequency is now divided by 2 power 3 times, right? So one way of dividing a frequency, one can use a counter and can choose particular bits to divide the frequency. Now if someone asks us to make so in this case it was like straightforward, you know, there is 2 power 3. Because suppose someone is asking us to make divide this 50 megahertz clock signal, use the, or they say that if use this 50 megahertz signal and just make a 1 hertz, divide this 50 megahertz to 1 hertz, then what we can do is then we need to design a mod 50 into 10 power 6 counter. Okay, so how to design a mod 50 10 power 6, maybe it's a bit beyond the scope of this discussion, but if somebody is interested I can tell this later, right? Okay, so now I'm going to explain the polling latency with help of a small example and an analogy. So in the lecture I was telling about a small analogy where I said that there is a bus stop, okay, and always there is a bus comes at 9 a.m. and then it leaves by 9:05 a.m. okay. Now this is the bus, let's start the bus. Now, and there is a door in this bus which opens, which there's only one door to enter in this bus, and this bus driver is a very strict guy, okay. He exactly comes by 9 a.m. and he will exactly leave by 9:05 a.m. and the other thing what he does is he opens the door of this bus only for a 30 seconds of time. So if there are passengers during the 30 seconds of time to enter, then they can enter inside, else they cannot enter. That means even if the bus is there in the bus stop and if the door is closed, you cannot enter inside. For instance, here comes Rama. Now Rama, one day he came by 9:01 a.m. and that way was a good lucky time for him. The bus driver opened the door at 9:02. and he exactly crossed after 30 seconds from this time 902, and Rama was able to get inside the bus. This is day 1. In another day, what happened? The bus driver came 9 a.m. and he opened the door exactly at 9 a.m. and he closed by 9:30, the next 30 seconds from 9 a.m. Okay, now poor Rama, what he did, he came by 9:01. Okay, but what happened is 30 seconds before, the bus driver already he opened the door and he closed. So the bus was there in the bus stop, the driver was there inside the bus, but the poor Rama was waiting outside the bus. He cannot get inside. So how much time he is waiting outside? So he is waiting outside the bus for 4 minutes, even though the bus was there. Okay, now another day, what happened, say this was the third day. In the third day, the bus came by 9 a.m. as usual, and the bus driver, he was in a nice mood. He was waiting for Rama, whether Rama will come. Then what happened is, he opened the door exactly at 9 o'clock 4 minute and 30th second. That means now he will close the door exactly at 9:05. Okay, and it was so coincidence, Rama somewhere appeared exactly at 9 o'clock and 4th minute and 30th second. So the moment the door was open and the Rama appearance was exactly same, and Rama was able to catch the bus. Now in this case 3, if you look into this, what was the waiting time of Rama? It was 0 seconds. It was so perfect. Okay, but in the case 2, the Rama was waiting for 4 minutes even though the bus was there, and what will happen is the bus also will go from this bus stop and he has to wait for next time when the bus can come again to the bus stop. Okay, so let's keep this analogy in our mind. Now let's go to the real microprocessor polling codes. Okay, so in the lecture we were seeing a small polling loop which was having a microprocessor instruction, something like what was that? Yeah, this was like there was an some address 2000, and then the next instruction was test. There was a test instruction with some number, and then there was a sum 0. So it was mentioned that this was 8t cycles and this will take 4t cycles, and it was said that if the sum 0 instruction is true, that means if it is true means we will go to the next step, we don't go back. So if it is true, it will take 4t cycles. If it is false, we will take 12t cycles. This was the question. This was some similar codes were there in the lecture, right? Now, as the similar time scale, this instruction, like how I was talking about the bus analogy, the time scale, what I was saying, like 9 o'clock to 9:05 a.m., this instruction also has a starting time and an ending time. Okay, these 8t cycles. The processor will take its time to execute this. So this is the starting time of this instruction. This is the ending time. Okay, this is end and this is start. Now what can happen is, say we were testing for some key press or something like that. That's the in value we are taking here. Say for example, we can actually press that key press when any time in between this. Okay, so suppose we press the key and the in instruction can, like how the bus driver was opening the door, the in instruction can read that signal any time in between the start and end time. We do not know when it will happen. Okay, say for instance, we'll talk about the best case. No, first we'll talk about the worst case. Let me talk about the worst case. So the worst case, let's talk about the worst case. So the worst case is how much time we will take to execute this. Oh. So so the worst case is you press the key and then your in instruction has missed to notify that. That means the in instruction, like, so when did I miss the bus? That was the case where the bus driver opened the door at the very beginning of the time, right? So let's say that the worst case, when the in instruction actually reads the value, the key press at this point, at the very beginning of the in execution time. So, and you press the key, and it was so that you pressed after this in instructions reading operation cycle, and you missed, and your processor missed to read this cycle. That means it has finished, but you have already pressed the key. You know that you have pressed that while the in instruction was actually doing its cycle, but the reading cycle is completed already, so you missed the bus. Okay, but you're still staying in the bus stop. Now if you want to catch the next bus, you have to wait in the bus stop until the next bus comes, right? The same way here, there were three instructions, right? The first one was in, and then the next one was test, and then next further on it was jump 0. So the in instruction, we wait for 80 cycles, and then we are testing it. That was another 40 cycles. That's what the problem we had here. And then the jump 0, this was a failure, so you will wait for 20 cycles. But what happened is, still you are waiting the bus stop. So when the bus comes again, you will get inside whenever it's getting open. The door is open nevertheless. So next time when the in operation happens, it takes another 80 cycles, and you will do a test operation, that's a 40 cycles, and jump 0, this time it is successful, so it will be just 40. So sum of all these t cycles will give you this worst time of this polling latency. Okay, now how we will calculate the best time? Now the best time is, let me write again, in, test, and jump 0. So these are three instructions, right? Now the best case is I have the same in operation, this is a time. Now if you see the best case, even in the bus analogy, it is like some miracle happen, that the opening time, the bus driver opened exactly 30 seconds before he used to leave, and it was so coincident that I just appeared right at the time and I could catch the bus without waiting. So such similar thing happens. The in instruction is reading the input from that port, whatever the, sorry, from this address, whatever we were having in that example, at almost exactly at the end of its cycle. Okay, and the key press also happened exactly at that moment, and you didn't wait for that in cycle. So you didn't wait for that 80 cycles, but you are now going to do a test. 40 plus jump 0 will be another 40 cycles, which is just 80. So this is the best case. Okay, so similarly in your lab 2, after you finish writing your codes, you will see the equivalent assembly language instructions. You will also you need to figure out where this kind of in instructions, for example in your case it will be load instruction, and something similar to jump 0, it will be some branch instruction or something similar may be there. So the codes between them is actually causing the polling latency. So you can use single step mode in while compiling. After you compile it, use the single step mode and see which are the instructions you are actually passing through, and that should actually give you the instructions which are responsible for the service. And then later on you need to find out which are the instructions you need to neglect to calculate the best case, which are the instructions you need to include for the worst case. Theoretically you will find these values, and then you need to do a practical verification using an oscilloscope. You need to connect these GPIO pins, both the reference and the pin which is coming from the NEOS processor, and you should calculate that practically. Okay, good.